Okay, so what I've got here is got a wheel. It's not slipping at A. Okay, I want to find the speed of the 10 kilogram block after 2 seconds when everything's released from rest. Okay, the wheel's got a weight and a radius of gyration given. Okay, so yeah, so again we've got time, velocity. So we're going to use momentum. So we'll start with the. We'll just draw them right on there since I'm being nice and lazy. Okay, so I've got a tension in the cable acting straight up. Got a weight in this guy of 10 pounds, right? So my momentum equation on this guy, again, everything's constant. The only thing acting here is gravity. So I've got t times 2 seconds acting straight up minus 10 times 2 seconds acting straight down. Okay, maybe I should say this is mv plus the sum of the FDT equals mv2, right? Starts at rest, so that goes to 0. So I've got force up, weight down, okay? And that's going to equal the mass of that guy, which is 10 divided by 32.2 times its velocity, which I'll just call the velocity. So one equation, two unknowns. Okay. Heading up to the top guy, I've got that same tension acting right there. Right. I've got the weight of this guy, which is 30 pounds, acting straight down. I've got a normal. Oops. Let's draw it all the way up. Normal force right there. And then if that's pulling to the left, friction has to be acting to the right. So I'll have a friction force right there. Now, here's the thing on this, and here's the thing to recognize. At this point right here, okay, there is no motion, right? So I can apply this equation, but instead of IG, I'm going to do it about point A, right? That point of contact. And again, I can do that because at this instant, that is a point of pure rotation. Now, a split instant later, that's not going to be the case, okay? But for this specific case, right at the point of contact, we know there's no motion, so it's a point of pure rotation. So call that I omega 1 plus any angular impulses that I've got equals IA omega 2. Now again, this guy starts from rest, that goes to 0. But now about that point, I only have that tension, right? Friction, normal force, weight all go to 0. All have 0 moment about it. So the only thing I have is 3 feet times that 10 times 2 seconds. And that's going to equal the moment of inertia. But now this time I got to take the moment of inertia of this guy about point A, which is going to be 30 divided by 32.2 times 1.3 squared. That's the moment of inertia about its centroid. So now I have to do that parallel axis theorem. So it'll be plus 30 divided by 32.2 times the distance away, which is just going to be 1 foot squared. So again, remember, you can some moments about either the center of gravity or a point of pure rotation. At this instant, the point of pure rotation is at that contact point, so I can use that. Okay, just remember to use your moment of inertia about that point as opposed to about the centroid. Now, omega 2, well, again, because of that point of pure rotation, I know the cable is moving at a velocity. Okay, so about that point, okay, that velocity equals 3 feet times omega. So the omega that I can use here is then v divided by 3. So now I have two equations, one with, or them both with t and v in it, okay? And I can find that the tension equals 4.73 pounds. And from that, I can determine that the velocity after 2 seconds is going to be 34 feet per second. Okay, so again, the key thing on here is recognizing that with rolling out slipping, I can do the momentum, the angular momentum about that point of contact, because there's no motion at that point, and I have a point of pure rotation. I just have to be careful with my moment of inertia when doing that.